Welcome to the Preliminary Cost Estimating Tool training series. In this video, we'll be covering the drainage section. Alright, so to start with the drainage section, we have to come down here to the drainage pull down tab and select yes to include the drainage part of the estimate. So here's the drainage section, and it's actually made up of three distinct parts: closed drainage, open drainage, and cleaning. The first inputs here up here on the top are the IDF and pipe material. So the IDF curve is actually a list of IDF curves for the region that was previously selected within the data entry tab. So for this example project, we selected region 1, and these are all the IDF curves for region 1. And for this project, I'll be selecting Albany. The next cell over will populate the applicable 5-minute 10-year frequency for that particular IDF curve. So for Albany, the 10-year 5-minute value is 6.42 inches per hour. This value will be used in the hydraulic calculations for the pipe capacity and spread calculations. The next input required is the pipe material. The pipe material selected here will be a default pipe material that will be used throughout the project, but it is important to note that this selection can be overridden at a more local scale further in the tool. So for this project, I'll be selecting SICPP. As we move down the worksheet, we'll see the first drainage system A. Each drainage system allows the user to add closed or open drainage, or a combination of both, to a single roadway. Each system can be defined with independent parameters such as terrain, cover, roadway with roadway classification, average road width, closed drainage length, open drainage length, shoulder width, and shoulder slope, as well as the number of outlets for each closed system. Some of these values will automatically populate based off the roadway classification, such as closed and open drainage length. For classifications with the urban classification, the closed drainage length is automatically calculated and summed up with the length values earlier defined in the data entry tab. For open drainage, the same is true, but for rural classifications. Both of these values can be overridden here with these light blue cells. The average road width uses the roadway description and averages the entire pavement width from the previously entered typical sections from above. Moving down, you'll find an open drainage segment where a user can define driveway crossings and culvert crossings. Both of these inputs can utilize a quantity of driveway crossings, average road width, pipe material, culvert diameters, and pipe cover. Using or inputting these values, the calculator will automatically calculate the length of the culvert required, the amount of excavation select fill needed for the pipe diameter and length, the number of end sections required, and in terms of driveway crossings, it will already size and count the amount of safety grates required. I'm going to scroll back up here and we'll start to enter in some inputs into this drainage system. The first input to select is the terrain input. The user can select a terrain value with the terrain drop-down list. This value is the same value used within the design criteria table found in design reports. This value is used in two separate calculations. The first calculation is the Puddle Spread, and this assumes a longitudinal slope while the second calculation is for pipe capacity, and this assumes a specific pipe slope. The terrain override, the cell right below, is used only to override the longitudinal slope for the puddle spread calculation. So if you know a specific profile slope, you can further refine the longitudinal slope for your puddle spread. For now, I'm going to select the level terrain. This will automatically input like we said, a longitudinal slope and pipe slope later on. So moving on over, the pipe material, this is really just looking at the pipe material you had selected earlier. Average cover, this is a little trickier to explain, so I have a diagram that I've drafted up to help better show and visualize. So here at the bottom, you'll see a generic profile of a pipe run. So what it really is doing is it's assuming in all terrain cases that the ground is level and the pipe is along the length is getting 0.5% deeper compared to the final grade. This is just an assumption. Again, we have no ability to track, undulations in terrain, high spots, low spots, pipes bucking grade. There really isn't a way to capture that in this preliminary stage. So, in order to get a better quantity on excavation, I just assumed that the pipe was generally getting deeper as the length got as you increased in length with a rate of 0.5%. So you'll find that as you increase your closed drainage length, that this value will increase. The 2.5 feet that you see as a default value is just really based on the HDM Chapter 8's minimum value of 2.5 feet. So right now we have a closed drainage system that is theoretically 0. Therefore, the average cover right now is calculated to 2.5 feet, since that's, again, the minimum. So the next cell down is the depth override. This will override all depths to a single value. This means that all the structures within the network, all pipes within the same network will default to this one value. And so if you look at the diagram here, that is what's represented by this dashed red line. So you'll see that if you put a value into this, that's what that value will represent. So all structures, again, all pipes will be overridden to this number. This could be useful if you have, if you're trying to do a more micro approach to laying this out, or for instance, that this closed drainage system is small, and you just want to, or you've already done the slope calculation and all right, well, you're starting from here, you're ending here, and you already know that your average depth is X. Well, that's what this allows you to do. It allows you to override the automatic calculation that we've previously achieved. So for this example, I'm just going to allow the average cover to automatically calculate, so I can at least show you how that's happening and how that's working into the excavation quantities. So we'll move down here. The next section to select, and this is very important that we do this because the program or the table down here will not populate until this is defined. So this roadway section actually is a list of the available roadways we had defined earlier in the data entry tab. So if we go ahead and select a New York 123, for instance, I know that this is an interstate classified. I think it's urban interstates. Let's see here. So 1, 2, 3, 11 urban principal arterial interstate. All right. So this is that value is used in two separate locations within this this table. The first is, again, any urban classified road will automatically sum all the sections from here. So if you have multiple typical sections for the same road, it will sum all these lengths for that roadway and add them to this value. Again, that's just for urban function classifications. The same thing will happen here for all rural function classifications. Now this is assuming that you'll need either closed drainage or open drainage for the entire length of the applicable function classification. The user can also directly override these values here. So if you had, we have 2,000 feet for closed drainage for this urban principal arterial interstate. If we wanted to do half open, half closed, you can easily just put in 1,000 here, and then 1,000 here. So you'll see that that automatically was taken into account for the sizing, the pipe sizing right here. We'll take that out. You'll see that the overall length increased. The backup for one cell, the average road width. This is similar to the closed drainage length. What this does is it looks up, this New York 123, looks at the typical sections where New York 123 is used and averages the width of this road. So it's averaging, for divided highways, it will average the A, B, and C, sum those. It will sum the E, F, and G, and it will basically average the width, the pavement widths for all the typical sections used for that roadway. So in this case, it's coming up with 72. Closed drainage. This is a very simple average width times the closed drainage length. So this will basically just be, if we looked at for instance, the rational equation, Q equals CIA, this would be the A in square footage. But the equation actually, it's CIA, A being in acres. So that would automatically get converted in the capacity calculations. The shoulder width is, again, that's going to be just a lookup. So it's going to look at New York 123, look for the shoulder quantities. I think this is actually a minimum quantity. So look for the smallest shoulder width in order to be a more conservative approach. So it's going to basically just look up the minimum shoulder width for in the typical sections for a roadway of New York 123. The shoulder slope is not defined in the typical sections, so this is just a default value that we've entered just to get the equation to run. This obviously can be overridden if you have a shoulder slope that other than 6%, 2%, whatever. The shoulder, it's also important to note that the shoulder width and shoulder slope with the classification go into the spread calculation. I'll get into that a little more, but if you wanted to play around with, for instance, your inlet spacing, basically inlet spacing is going to be defined by your spread, which is defined by these two values here, along with, like we said before, the terrain value. All right, so coming down to the the number of outlets within the drainage system. The number of outlets, like we can go back to this diagram here. The diagram shows two drainage networks. One has a singular outlet found here, and another one has two outlets, one here and one here. So all this really is doing is it's splitting up the network into sub-networks. This is very handy for roadways where you might be required to drain, let's say a mile. Well, in all practicality, you'll never have, or should never have, a drainage network that is a mile or 2 miles in length. You would get very deep, and the pipe size would get insanely large. So in order to help alleviate this in the preliminary stage, I've assigned a number of outlets input here, which basically just splits the network evenly. So if we put 2 number of outlets, that basically just splits the network so that there are 2 areas, the closed drainage area, and the calculation the background calculations are halved, while the pipe diameters are multiplied. So you'll see here, if I go back to 1, we go all the way up to a 30-inch pipe, whereas if I put in a intermediate outlet, we no longer need a 30-inch pipe. Furthermore, you'll see the pipe lengths will double essentially. So we had 18 inches we had 1,300 feet of 18-inch pipe here. So if we put in an intermediate outlet, we now have 2,000 feet of 18-inch pipe. All right, so moving along, the next group of cells here, this is going to be your typical runoff calculation. So this is purely, again, a rational method, Q equals CIA, where it's multiplying, it's assuming that the entire closed drainage area, this is pavement. So it's using a C of 0.98. With I is the intensity, which is this value here, times this in acres, not square feet, but acres. So that's how this is generating the 20.8 CFS. So this is the value that's going to be injected into this table in order to size the system. The next value here is the max spread. This is actually going to be it's going to be a simple lookup, so that it will look at the roadways, again, the roadway classification, and determine what the max puddle spread can be without busting your HDM Chapter 8, Section 744. So basically, that section defines, that a interstate requires the puddle spread not to exceed the travel lane, or actually not to exceed the shoulder, so it does not go into the travel lane. But all roadways other than interstate or freeway, you're allowed up to half the travel lane width. So what this is going to do is this is automatically going to limit your puddle spread to this value if you're in an interstate classification. If you're not in an interstate classification, this will go to the shoulder width plus 1/2 of one travel lane. So for instance, I know for New York 123, that's an interstate, therefore the shoulder width 5 feet is being held as the max puddle spread. Now if I go ahead and change Main Street, which I know is not a freeway, you'll see that we've gained 2.5 feet of allowable puddle spread, because we can now go half a lane into for your puddle. That's great. Let's just go change this back. All right, so continuing on, the suggested inlet spacing is another kind of complicated process. So what this is doing is it's going and taking your max spread calculation, So if you looked at your spread calculation, you usually I believe solve for T. Actually, I take it back. You might solve for Q, but either way, what the equation is going to do is going to rearrange it in order to solve for T, and it's going to set 5 equal to your spread. So it's going to come up with actually a Q. So this is theoretically your max flow that your spread, your max spread can handle without exceeding that HDM chapter 8 allowable distance. So again, this is going to be a max Q, and then what it does is it goes and plugs that Q into a CIA equation, and then back calculates to an A. So then in theory we'll have a area that is it's a maximum area that is allowed before, again, you allowed to drain to before you exceed this max A, or max spread. The spacing, the A is then divided by an average width of 72 to get a theoretical linear length that is allowed between each inlet in order to meet your max spread. So, a spread calculation uses, the shoulder slope, which is a transverse slope. Again, your shoulder width. So I'll play around with this to show exactly what's going on here. This value is also capped at 300 feet. So if your calculation of your max spread is greater than 300 feet, or allowed distance is greater than 300 feet, you'll just see 300 no matter what you do. But I know a couple of values that I can do in order to get that below. For instance, if I drop this, I think, to 2%. 2%. You'll see that now we're only allowed 87 linear feet before of inlet spacing before each inlet exceeds the 5-foot puddle spread. This is also taking into account a crown section. So it's really the area divided. It's the area divided by this divided by 2 to account for a crown centerline section. So we can play around. If I changed this New York 123 again. Let's go back to Main Street where we have maybe a greater max spread width. You'll see that now we can go 300 feet. Which makes sense because we are allowed a greater puddle spread. So again, let's go back to 123. At 2%, you can only do 87. All right, well, let's add some more shoulder width to this. Let's make it 10 feet instead of 5. So we put in 10. Now we can exceed. Now we can go past or go up to 300 feet. And I think we're good to go. So this is kind of just a very preliminary step. Again, it's utilizing the typical section values that we've entered before, as well as a kind of default 6% shoulder slope typically used around the state. But we're going to move down to the sizing of the closed drainage system. This is what this table here it does. So the start will be, let me just go ahead and delete that. But to start, I'm going to basically go through some of these calculations, tell you, what's going on here. These default pipe diameters are placed, so they're really just placeholders. If you want, you can go ahead and override these to anything you'd like. I think so if you go to 24, you'll see that the rest of the pipe diameters will update so that these these will always be in ascending order, and they have to be in ascending order for this table to work. So moving on, this upstream CFS value, so that's going to equal how much flow is coming in from the upstream segments. So this can account for, if you're building a closed drainage system, and there's you're linking into maybe an existing system upstream, or even halfway through your proposed system, maybe there's a branch that's coming in that you have to take care of. This is where you can go ahead and input some of those flows. For instance, here we're starting with a new system at the start. So right now it's 0, and by default when you have 18, that's what that value is going to be. For this tool, 18 is as small as it can go. You can adjust these diameters later in the backup to whatever value you'd like, but for this hydraulic analysis and for the very, very preliminary data entry tab, we're just going to stick with the smallest value of 18 inches. So this upstream, and if you go ahead and select maybe let's just say a 24 inch. So, if I'm coming in and I know there's an 18 inch pipe upstream, and we'll just start with the 24 down as the first proposed pipe, we'll go ahead and put 24 in, and you'll see that this upstream value populates. So this upstream value is actually equal to the next lowest pipe diameter, as if it was running full or flowing full. So this is basically an 18 inch full flow pipe coming in to a 24 inch pipe, and the rest of these calculations are based off that assumption. So all the flows that are injected with that assumption. Moving over, local flow is equal to the pipe capacity under the given conditions. For instance, pipe slope's taken into account, the 18 inches taken into account, pipe material, all that stuff is assumed to be mannings of, I think, 0.013 or something like that. Not to want to get any technically crazy, but so local flow is basically this pipe's capacity. Pipe length, this is a little weirder. This is calculations based off of I think this value, and it basically takes the local CFS, puts it into a CIA equation to come up with an area. The area is then divided by, again, the average width to come up with the linear length of theoretical trunk line. So to go back to this diagram here, so it would be the linear length of this pipe here. So for instance, 18 inches, 745 CFS can throw through an 18 inch pipe. So 745, we inject that into the CIA equation, come up with an area that theoretically is an area that 18 inch pipe can handle. And we then take that area and divide that by the width to come up again with a trunk line length. So that's, and on top of it, to drive a little further complication into it, we also take into account the crossing pipes, because the crossing pipes have to be accounted for. Crossing pipes are automatically added to the smallest pipe diameter in this table, so this row only. You'll notice that this is significantly larger than the rest of these. That is because every crossing pipe within the network is assumed to be an 18 inch pipe. Furthermore, the number of structures indicated is equal to the amount of times this inlet spacing, 300 feet, can fit within the previously calculated CIA equation or trunk line length. So the number of structures is basically just the spacing divided by the overall trunk line length of that given pipe diameter. Now remember, you got to times that by 2 in order to account for the structures on both sides of the road. So moving on, the downstream CFS is going to just be the upstream plus, so the upstream value plus the local capacity of that pipe will be the downstream, so the flow that's going downstream of the 18-inch pipe. So this value is then injected into the upstream flow for the preceding pipe size. So that is basically kind of like a budget. You know, you just transition that downstream to the next pipe going right here, and then that's deducted from the capacity of that 24-inch pipe in order to figure out, all right, well, the 24-inch pipe can handle an additional 8.59 CFS of the rest of that's coming down from the rest of the network. So then we just add the local upstream, do the same calculation we did before. Again, 826 linear feet of trunk line we can place with that 24-inch pipe and take in that additional area. The downstream will basically be just the 7.45 plus the 8.59 will be your downstream flow going to the next or 30-inch pipe. So then the 30-inch pipe will basically be handling a 16.04 coming from the upstream segments. So the 30-inch pipe can handle another 4.76 CFS. Now this is probably significantly less than the actual capacity of a 30-inch pipe because we've reached the end of the network and there's just no more area for the pipe to need to treat or convey. Again, that same area is calculated into the CIA equation to come up with an area and then a length. And that length is also used again to find the number of structures at that suggested inlet spacing. So that's basically how this table works. Again, all these light blue cells are overrides that you can manually enter. So if you again have, like say you have another 24-inch or some kind of flow coming in halfway through this network, if we go and override some of these values, you have to remember the override has to account for whatever's there right now. So if you had a branch coming in addition, halfway through this network at the 24-inch pipe segment, so if you had a branch coming in, you could, let's say if it was 2 CFS in addition, you have to add that manually in your head, so that, so if you had 2, that would make it 9.45 would be an override. So it's not an addition, it's overriding it completely. So you'll see here that this is now added. If we wanted to up that to, let's say 15 even. So you'll see that we need more 30-inch pipe to accommodate that additional flow. So that's basically the sizing table in a nutshell. It is complicated, but drainage, closed drainage, again is very site specific. It's very hard to come up with a preliminary estimate at this stage without doing extensive engineering and backup to account for. All right, so we're gonna move on to the open drainage segment. Open drainage is a lot more straightforward. Basically, it's more like you're given a quantity. You can enter quantity of driveway crossings. You can enter the average driveway width, and pipe material the driveway, the pipe diameter, and the pipe cover, and all these entered together. You can also override your pipe material if you want to use metal instead of plastic or anything other than what you had previously entered as a default value. All those inputs are generated, and we'll put some dummy inputs in here for now. So if we have five driveway crossings, let's say each driveway crossing is again, this is a pavement edge to pavement edge dimension. So it's going to automatically take into account kind of additional earth from the pavement edge to maybe the top of slope or top of embankment. It's also going to take into account, let's say we have a 2 foot, that's pretty deep driveway crossing. It's going to take into account the culvert length coming through that slope. So if we do 1, go a little less, perfect. So 1 foot, it's basically this pipe length is taken into account a 1-on-3 slope. So culverts, again, it's quantifying all the culvert quantities here. It's automatically calculating a item number based on your material and your diameter. So here 6039815 corresponds to the smooth interior corrugated plastic pipe item. So if we wanted to change this to let's say concrete, 6036002 will equate to the concrete equivalent. Now the one thing to keep in mind is not all pipe diameters are available in the material. So for instance, if I go to 21 inch, now I know 21 inch is available in a concrete, but it's not available with plastic. So if I select that, you're going to see an NA pop up for the last 2 digits. That has to be corrected. A unit price will not be able to calculate from this item. Therefore, you won't see that cost in the item list. So 24, that exists. 27 won't exist. So 18 inch corrugated plastic pipe, perfect. Excavation, this is going to use both the quantities and the lengths and all these inputs in order to assume a section, a trench section with the depth. So automatically it's calculating your total cubic yards of excavation, trench and culvert excavation. Same thing for select fill. End sections, it's going to basically just take the number of driveway quantities and times that by 2. Two end sections per crossing. Pretty straightforward. Safety grates. So here, safety grates are only calculated for driveway crossings. Safety grates really, they're really necessary when you have an end section that is perpendicular to the traveling direction. So this really, the theory is that driveway crossings, you're intersecting road at a more perpendicular angle than you might have for compared to a culvert crossing. So that's why safety grates are really only considered for driveway crossings. But again, this is automatically calculated based off the pipe diameter, because this is a square footage item. So it's automatically looking at the pipe diameter for the corresponding end section size, and then finding the needed square footage in order to cover that applicable end section, and then timesing that by the number of end sections there are. So it's a pretty straight lookup. Again, all these values can be overridden per the user's input. So if you want to put a little more fluff into it, if you know more of a direct input, or you know, you want to round some of these off, whatever, you can go ahead and do whatever you need to do in order to get the appropriate quantities in, and the tool will automatically take that into account and override any of these calculated values. So we'll move down to the culvert crossings. These are these inputs are just like the inputs we use for driveway crossings. Just the terminology is a little different. First, we have the quantity of culvert crossings, so the number of culverts that you're crossing your roadway. Average crossing length, culvert material, culvert diameter, pipe cover. Again, it's all the same as driveway crossings, just different terminology to do the same thing. So we'll go ahead and enter a couple of values here. So we'll go to quantity, culvert quantity is 3, so we have 3 crossings. Say we have an average length of 30 feet, seems like a pretty round number. I know this is actually an interstate section, so I think the interstate section is like something. Let's just say 800. Let's up this 100, just to be consistent. So 3. Let's go with concrete, beefier. Let's go with a 30-inch section. Pipe cover. Let's go to 5 feet. All right. So down here we find the same values, same calculations as before. 603.6007 is the item for a 30-inch concrete pipe. So that checks out. 360 feet of it has been calculated. Again, it's taken into account the embankment side slope and additional. It's assuming an additional earth from the top of slope to the edge of pavement. Excavation, you know, again, it's taken into the length of pipe, the amount of pipe, or the quantity of crossings, and the cover. So select fill. Again, it's the same, pretty much the same as the excavation, but of course, per the standard sheets, it's just around the pipe. End sections, all we're really doing again is taking the culvert quantity timesing by 2. Want 2 for each crossing. So I'm gonna go ahead and put some overrides in here. Let's just assume, you know, let's make it an even number. Assume 400 feet, linear feet. We'll go ahead and round off some of these values so I can show you the overrides. 250, and we'll keep it at 6 since that's a hard one to run away from. So these values are automatically added and override these values. They do not override any of these. Everything's pretty much summed up in the back. All the culvert items and all the similar items are summed together. All the select fill is going to be summed together in this whole sheet. Same thing with excavation, and it's all going to be tabulated in the item list below. The last portion of this section is going to be cleaning. Cleaning is a very easy way to just make sure, you know, if you're not replacing or not replacing existing drainage pipes in your network or in a road, you can easily just go ahead and quantify some cleaning of the existing drainage systems. It's probably good practice to always include that in capital projects with an existing system. So, you know, let's say we have 2,000 feet of a code drainage system that's within the project limits that we're not replacing. Cleaning and shipping structures. Again, that's going to be in each, you know, typical values. Let's say 20, and then cleaning grade for open drainage. Let's cleaning grade of about a mile. So all these items are going to be included into the item list below. It's that simple. Lastly, you know, if the user wants to add a user-defined item, maybe the regions typically use a certain item for drainage. Maybe, you know, instead of, because I believe these are non-contaminated cleaning items, maybe they need to use contaminated cleaning items for some reason. Or, you know, they want to use specific type of pipe, you know, that's not included in this tool, arch, or some kind of different gauged metal pipe, whatever have you, or different structures, you know. Those can be added. Those can be added here as the user sees fit. You can use these minus and plus tools to just add more as you need them. So I'm going to scroll right back up here and show you how to add maybe another drainage system for a separate roadway. You know, it'd be good because the inputs won't be the same, the function class won't be the same, all that stuff will look a little different, but it's very important to know that, you know, where these things are coming from, how it's recalculating. Again, we'll you know, go with the level, keep the level over or terrain override the same. Pipe material SICPP, okay. Average cover. Now it's copied this, so the first value you see here is just going to be a duplicate. But if we go ahead and change this Main Street, now I know it, function classification is going to be an urban collector. Urban collector. All right, so we know that the tool, since it's urban, is going to automatically define. It's going to automatically populate the 1,000 feet within the closed drainage system. So, you know, I know, for instance, that the side street is considered a rural roadway. Has a rural classification. So if I selected that, you can see that automatically is populated in the open drainage section. So again, there's that rural and urban classification determining, you know, what by default is going to be closed drainage and what is open drainage. So let's go back to Main Street. Let's, for the hell of it, let's override this to be 750 feet. So we know, for instance, if there's, let's say, 750 feet worth of curbed road, where remaining 250 is considered open drainage. This value doesn't really do much further downstream. It actually used to populate and calculate when in here, but for our user suggestions or testing phase, we found that, you know, that necessarily wasn't most user. It wasn't very helpful. So just to keep track of it, 750, 250, you'll see that this is calculated just based off this 750 times 36, so it equals 27,000 square feet. Per the typical sections, on Main Street, we're still using a 5-foot shoulder. Again, by default, it's a 6-foot slope, or 6% slope. There's no reason really, I think, to again add another outlet here. We only have 750 feet. That should be easy enough to handle with one segment of one subnetwork of pipe. So again, the runoff is automatically calculated from the area and the intensity curve earlier selected. Max spread, again, automatically calculated based off the function classification. So we have, it is not an interstate or freeway. So we have 5 feet plus another 5.5 or half a travel lane equals 10.5 feet for max puddle spread. Max puddle spread is then, again, inputted into the suggested inlet spacing, which is just a glorified spread calculation. So it's going to set the spread equal to the 10.5 feet and come up with a linear length of road that a inlet can see, it can drain without exceeding this 10.5 feet puddle spread. Again, that is maxed at 300 feet. So in reality, you might be able to see a lot more, but per HDM Chapter 8, 300 feet is typically the maximum inlet spacing or manhole spacing you can have. All right, so you can see here it's automatically calculated an 18-inch pipe at 858 feet linear feet. Again, this is taking into account all the crossing pipes required. So there's 3 crossings, 2 structures for each crossing. And all really, just to clarify, the crossing pipe length really it's just this. It's just 36 feet. So 36 times 3 plus that linear length we had come up with for the initial sizing is what this 858 feet is. So at the first stab, this looks pretty good, just as if it was all completely proposed. Now throw a little wrench into it. Let's just assume that in this particular spot on Main Street that there is another 18-inch pipe that we're tying into. So for this preliminary phase, since we really don't have any good handle on existing flows, you haven't done any kind of drainage watershed work on it, we haven't delineated any watersheds, we're just going to go and assume that we need to automatically upsize to the next size bigger in order to maintain the existing capacity upstream. So let's go and just manually put in 24 inches. Now you'll see that this upstream flow is automatically calculated. So again, this is a 7.45. So this is the maximum flow an 18-inch pipe can see. So 7.45 is injected at the start of this 24-inch pipe. And we can still maintain 858 feet. So the 24-inch pipe can still maintain a full 18-inch pipe plus the local flow, which is basically the proposed area from this 27,000 feet that's coming to this new 24-inch pipe. So we're still pretty good. So keep in mind, that this is only a 36-foot wide road compared to a 72-foot wide road. So it takes a lot more distance in order to exceed the area that a 24-inch pipe can handle. So 5,000, 36, 180,000 square feet. All right. So you can see if we started off with 24-inch to maintain the existing 18-inch coming into it, we need 2174 linear feet of pipe, and then 16.04 will dump down to the next highest pipe is 30-inch, and then 1304 will be provided to the 30-inch pipe locally, and that will take care of the rest of the area. I'm gonna quickly go ahead and change the level just to show you. So say Main Street isn't level. Say it's a rolling. The rolling is going to change two things here. It's going to change the spread calculation because of that longitudinal slope. It's also going to steepen the pipe capacity because theoretically, if you're in a rolling terrain, you don't need to run at a minimum pitch. You might be able to run at 1% or more, depending on without busting through grade or making your excavation unnecessarily deep. So we're gonna go with rolling. And you'll see that the capacity has changed. So no longer is it, let's see, go back here. So no longer is the 24-inch only handling 8.59, but now the 24-inch can handle 12.15. Similarly, the 30-inch no longer could handle 1304, it can handle a little more. Actually, it goes at 1385. But you might see this segment go down. So you'll see that the amount of pipe here, so you see the amount of linear feet required for a 30-inch pipe, and the number of structures. We'll go ahead and remove some of this stuff that I wanted to test out. Move that. We don't have open drainage. All this stuff is, and all this stuff is removed. All right. So we have two roadway sections in here. Of it, we can add one more. So this will be, like I said, side street, which I know is our rural. Go back to the top here to get an actual classification. Local, rural, side street, rural, local. Okay. So here, theoretically, spread, all that kind of good closed drainage stuff does not apply, even though it still might be calculated. It won't be used in the actual summation of items or quantities. We'll just have to manually enter some of these open drainage as we see fit. We see that 1500 is automatically injected into the open drainage. So, let's just start out from the bottom. Let's clean all 1500 square linear feet of ditch. Get that in there. We have 1500. Let's say we have 10-ish. 150 feet. Yeah. Let's say 5. Let's say we have 5 driveway crossings. It's a good number. Average driveway width, we'll stick with the typical 12 feet. It could be 11, whatever, 24, big driveways. Go with metal. Go with culvert diameter in 12 inches. That does not apply. Look at that. See, the metal is not. So the other thing with the metal is that because we have to stick with I wanted to stick with a gauge that covered the most amount of diameters. Might not have some of the gauges for certain sizes, so just keep that in mind. Let's go with pipe cover of 5 feet. I'm sorry, this is a driveway, so 1.5. So this is a cover also. So it is basically from finished grade to the top of pipe. So that's also, so you're not accounting for the pipe diameter in this input. Pipe diameter is accounted for when it starts to calculate excavation / fill. So here we have some generic quantities that's calculated. We're just gonna roll with it. Put in one single culvert crossing for an average crossing length of, this is a rural street, so it's 30 feet again. Culvert diameter is, let's go with 24. It's good size. Let's say 2.5. Let's say 3 feet. 3 feet. 3 feet of cover. material is going to be SICP concrete. And again, there are your quantities. Going to be added to the cost. So that's the drainage section. You know, if you haven't gone through drainage design previously, some of this stuff can be confusing. Just stick with it. I put a lot of notes in to help guide users unfamiliar with this along. I think the one takeaway in order to get this thing to work, the minimum inputs required to get at least something is going to be the IDF curve, the pipe material, the terrain, and the roadway. Those three inputs have to be assigned in order to get the worksheet to at least spit out the closed drainage. Now, if the roadway is a rural roadway, the closed drainage will not populate because it's a rural classification. The open drainage will not automatically calculate. You must come down here and assign these values. I don't think it's very cumbersome to do, but you can enter these 4 values in, and at least it'll spit up something that you can include in the preliminary estimate. And this is just a placeholder. This is not a site-specific number. It's just to get a count for the drainage cost. That is it. It is by no means a full stop designer. So I hope this was useful. The backup tab right here has a lot more power behind it. You can definitely do some more custom tweaking there, and I'll have a training video to cover that shortly. Alright, so we're gonna jump to the worksheet or backup tab for the drainage section. I'm just gonna go up here and click this link. The link will send us to the drainage tab, and here's a couple of tables that represent the pipes, structures, the open drainage, and any additional items here that are actually brought in from the data entry tab that we had just filled out. So the site data up here, this is more of a reference, a visual reference for you, just to show the county, the IDF curve, the 10-year intensity and the 25-year intensity. In this backup tab, there actually isn't any kind of hydraulic calculations being done. All that was done in the data entry tab. The backup tab for the drainage section is purely for quantity calculations. Several overrides exist here. Item structures for items, that kind of stuff. So again, there's no hydraulic calculations being done. I guess we'll just go ahead and start off with the pipe section here. So this is basically provides a summary of what the data entry tab calculated. You'll see all the various pipe diameters here with the applicable materials, the pipe items, the length, depth. Both of those are calculated from the data entry tab, and then the equivalent amount of excavation select fill for each diameter pipe. So all these light blue cells designate an override spot that we can go ahead and override those selected quantities or items. So for instance, let's go to the 24-inch pipe here, and we'll quickly go ahead and override that particular 24-inch pipe. So let's say concrete. So you can see how the pipe item here manually automatically took into that override and adjusted itself to indicate the 24-inch concrete pipe. And then if we also go to if we wanted to change the total amount, say we don't need 1,330 or 1,330 feet of concrete pipe, so we only need 1,000. We can go ahead and plug in 1,000 here. The depth, excavation, and select will automatically recalculate based on that quantity. Now remember, the depth is from that diagram that we had shown earlier, where it is averaging the depth in conjunction with a typical pipe getting about 0.5% deeper compared to the proposed or existing grade. So in that sense, we shortened it up. We went from 1,300 feet to 1,000 feet, so our average depth decreased. Similarly, excavation and select fill, that utilizes that depth to in turn calculate the amount of excavation required for that 24-inch pipe. Similarly, select fill also uses a 24-inch pipe, and both excavation and select fill utilize a trenching section similar to what is found for the standard trenching detail found on the standard sheets. I believe it does use method A, which is kind of like a standard method, where you're all you're really doing is you're excavating in an existing grade, inserting or installing the pipe, and then backfilling. Pretty simple. So those are the overrides for the pipes. That's how that works, and all that gets calculated and computed and summarized into the item list below. All right, so moving on to the structures. Again, the structures automatically populate here, and they actually utilize the diameter, the pipe diameters, to automatically calculate what structures go with what item. For instance, the 600603 item is, I believe, a type F structure. So it's a 48 by 48 inch square structure. Now keep in mind, all of these structures that populate here are going to be the square versions. There won't be any kind of type B or type G structures where the one side, or the length or the width, will be at a different dimension than the reverse, than the length or width. This is so that this tool doesn't have to take into account orientation. It's really hard to kind of get in Excel to calculate that kind of stuff, and for, again, preliminary stages, just getting a structure with an appropriate item in here is probably good enough for this stage of an estimate. So to keep that in mind, the item that the structure is identified under indicates the pipe size. So we're taking into account the minimum, or I should say maximum pipe size a given structure can successfully connect to. I believe a 30-inch pipe is the biggest a type F structure can successfully handle. So if we were to come in here and manually enter, hopefully this works. If we come in here and manually enter a 36-inch pipe, so let's say we have 100 feet of it, you'll see that another structure here will populate. Now, it doesn't have any idea of how many there are, because that number of structure calculation is done in the front in the data entry, but it will automatically assign that pipe to this structure. So anything that's done in the data entry tab, all those assumptions and all those calculations are taken into account when we're generating structure items. Furthermore, each structure, each segment of pipe up here generates a depth, and that also is in turn used when determining the height of each structure. So the height is actually the average depth of the applicable diameter pipes. So for instance, the type F structure here, 30063, that average is actually the average of 7, 9.93, and 10.18 in a weighted average, because it has to take into account the linear footage into account. So, I'm sorry, I actually misspoke. So it does not include the 10.18 because that's a 36-inch pipe, and therefore would not be able to work with a type F structure. So it's just the average of 7.7 and 9.93. All right. So moving on. So the structure, again, now if the user wants to utilize structures other than those square ones I had mentioned before, they can go ahead and override this item and plug in any item they see fit. If it's a type M, whatever. You just have to. They would just have to manually enter in those items. Same thing goes for round structures. If you don't want a round structure, you have to manually enter the structure item number here. Moving down, again, this is going to be a sum of what is coming back from the data entry tab. So in the data entry, it summarized 14 structures for the whole page. Again, the average height I mentioned before is from these two items, or the applicable pipe diameter. Excavation, again, it's going to use the standard sheets to calculate excavation select fill. So typically that's going to be a 2-foot wide trench all the way around the structure. Same thing with the select fill. And then the grate item. The grate item is going to be just it's going to be just a placeholder. For now, it's I think one of the more costly ones. By default, it's like it says here, the grate item is an F3 cast frame with a curb box with a G3 reticuline grate. This is probably the most beefy, biggest item grate that's out there. So hopefully, by default, we're already capturing the most expensive thing we can find. Therefore, if the user wants to go ahead and override it with a different grate, say one without a curb box, they can manually enter in the grate item, and that will also be summed up in the item list below, and it'll automatically generate an item cost. So all the rest of these overrides are pretty self-explanatory. You can override number of structures, the height of each structure. Again, there's no way of separating the heights across the 14 different structures. It's more like this is going to be the average height for all 14 structures. All right, so this excavation and select fill number is actually for the entire project across all 14 structures. So just keep that in mind when we're adjusting these numbers, that this is a small adjustment here might necessarily totalize a big difference per structure. All right, so moving ahead, we come down here to the open drainage section. Now the open drainage section is going to summarize per pipe size all the quantities again in the data entry tab. Now all these pipe sizes are summarized from both the driveway and culvert crossing sections. Therefore, if you have an 18-inch driveway crossing and an 18-inch culvert crossing of the same material, they will be summed in one row. Therefore, if you change one and not the other, don't expect, or you delete one and not the other, don't expect the change to carry directly over to here. It will change here, but just keep in mind that these are summed values and are not a direct one-to-one reference. So we can see here that we have already located 18-inch pipe, metal with the proper item number, the pipe quantity in feet, the excavation, and the select fill. So again, we see 24, a 30, and another 18, but this is still plastic. The pipe quantity, excavation, select fill values, again, can be overridden here if you wanted to add some fluff, round up the numbers, what have you, or if you think this is a little, this particular location might be more complex than what what's taken into account in this estimate. These items can be adjusted per your direction. All right, so one of the last remaining bits here, again, is the cleaning. Again, the blue cells are directly from the data entry tab. So this is basically just summarizing the data entry tab. And then we can go ahead and override those further if we need to. The additional items here, this is going to be where we can go and add in additional items if we see fit. If there's some regional items that are typically added or included within projects, you can add these in right here. You can add any number of them in by using the X or the X and the plus here. So again, that's pretty self-explanatory. The item number, you can enter the item number here with the quantity, the unit, and any notes. This won't be a item description. This will be a user-defined notes. So if you needed to provide some kind of additional backup, or you wanted to have a note to yourself or maybe a reviewer of why you put this in, this would be a good spot to do that. And then lastly, we have a generated item list here with everything that we've put in for both the backup overrides and the data entry. So this gives you a nice summary of quantities generated from the data entry and the backup in a format that's more familiar with an engineer's estimate. So the unit prices are actually automatically being generated from the item list tab. Earlier in the Excel file. So all that's being brought to this point, automatically generated, so you can quickly see the extended amount for each item. And that's it for the drainage section. If you have any questions, concerns, please reach out to me. Hopefully this was useful, and thank you very much for the training. And that concludes the drainage section segment of the Preliminary Cost Estimating Tool training series. For additional Preliminary Cost Estimating Tool training, be sure to check out our other videos. Thanks for watching.